Hello everyone, welcome to Classes with Atish. Today we'll talk about Laplace transform and maybe some of the applications of Laplace transform. This might need a couple of videos, but today would be an introduction to Laplace transform. Okay, so let me share my screen. So first of all, let's define what Laplace transform is. Like the name suggests, it is a transforming function. What do we transform and what do we transform it to? If we have a function, let's say f of t, this Laplace transform would transform this function f of t to another function f of the independent variable s. How do we do that? The notation for Laplace transform is L f of t is a function of f of s, and it is defined as integral minus infinity to infinity e to the power minus st ft dt. Okay, pretty simple definition. Now, there are several applications to Laplace transform, but primarily what we will discuss today is the application of Laplace transform to solve ordinary differential equations. Okay. But before we get to how we solve ordinary differential equations using Laplace transform, we need to little bit understand how this transform works and what is the transform for some common functions. Then it would get easier to apply it to solve ODEs. But the whole process here is we apply Laplace transform to an ordinary differential equation. What it does is it converts that differential equation, which is difficult to solve, to an algebraic equation. Okay. So when we have an algebraic equation, we can solve that algebraic equation, and then we apply a inverse Laplace transform to that algebraic equation to get a solution for the ordinary differential equation. So this is what we want to do. Okay. But let's talk about this in a little bit more detail now. Now, what I just mentioned here, when the integral is over minus infinity to infinity, this is called a bilateral Laplace transform. Okay. What would be an unilateral Laplace transform? It would be when the integral is over 0 to infinity. Okay. E to the power minus st ft dt. Okay. This is called unilateral Laplace transform. Okay. Now, unilateral Laplace transform is more commonly used than bilateral Laplace transform. So we will just stick to this, but the concept is similar. Okay. Now let's try to figure out maybe Laplace transforms for some of the common functions. Now what I will do is I will create a table. Let's say this will be the function of time, and then what would be the corresponding Laplace transform of f of t. Okay. Why we denote t is it is more a function of time, and then the Laplace transform is more a function of frequency. These are more applications of Laplace transform in real life physics problems, but that's why the donation of function of t and function of s. Okay, but we'll not get into those details right here. But let's continue. Okay, let's figure out what is the when ft is 1, what is the Laplace transform of the same. Okay, so this is problem number 1, let's say. Okay, so Laplace transform of 1, what would that be? Let's calculate that. 0 to infinity integral e to the power minus st 1 dt, which is nothing but what's the antiderivative of e to the power minus st? It is e to the power minus st minus 1 by s, and we calculate it over 0 to infinity. Okay. Now, if I take 1 by s minus 1 by s outside of the brackets, then this becomes a limit of e to the power minus st when t tends to infinity minus limit of e to the power minus st when t tends to 0. Now, we do have a problem here. If s is a negative number, then this will become divergent, which is the limit will become infinite. All right. So we really cannot find the Laplace transform of 1. But when s is greater than 0, then the limit is convergent. So let's calculate this when s is greater than 0. So 1 by s minus 1 by s outside the brackets. Now, if s is greater than 0, this is 1 by e to the power infinity, which is 0, minus this is 1 by e to the power 0, which is 1. So this is minus 1, and then minus and minus multiply, this becomes 1 by s. Okay, so Laplace transform of 1 is then 1 by s. Now, these are few the ones that we're writing down in this table. We'll have to memorize those. So that's where application of this becomes easier to solve the ordinary differential equations. Okay. Let's move on to the next function. We'll just pull this down. Okay. Let's do Laplace transform of e to the power at. So basically f of t is e to the power at. Okay. So what would that be? Integral 0 to infinity e to the power minus st times ft. Ft is now e to the power at dt. Okay. Now, this can be written as 0 to infinity e to the power, let's write it as minus s minus a. S minus a t dt. Okay. So what is the antiderivative of this? This will be e to the power minus s minus a t minus 1 by s minus a. And we are calculating this from 0 to infinity. Okay. Now, here we are again faced with a problem of convergence and divergence of this integral. So there are two cases. If s minus a is greater than 0, right, then this integral becomes convergent. We can solve this integral. If s minus a is less than 0, so what would happen is this term will become positive. S minus a is less than 0. So e to the power infinity will become like a big number. So this will become divergent. So we really don't have, we can't really solve this improper integral right here. Okay. So in the case when s minus a is greater than 0, let's see what the solution is. So let's take 1 by s minus a outside of the bracket. Then this becomes e to the power 1 by e to the power t. Now 1 by e to the power t as t tends to infinity will be 0 minus, it will be e to the power 0, so which is 1. Okay. Now this will evaluate to 1 by s minus a. Okay. So we can now write Laplace transform of e to the power at is 1 by s minus a. So if you can see here, what happens is when we multiply a function ft by e to the power at, there is a shift, or let's say when we multiply 1 by e to the power at, there is a shift in the solution. It is as if it becomes function of s minus a. Okay, we'll talk more about this with examples later, but just look at the shifting pattern. The other thing is, if a is equals to 0, then this evaluates to 1, which is this function, and this evaluates to 1 by s. So we are consistent. Okay. All right, let's take the next example. As we build out this table, I just want to keep this in perspective, so I'm putting this down here. Okay. Okay. Number 3. Let's look at the next function that we can find the Laplace transform of. Let's do Laplace transform of sine at. Okay. So as per definition, integral 0 to infinity e to the power minus st sine at dt. Now, these type of problems, how we will solve is using the integration by parts. And just to revise few things, differential of two functions u dot v or uv is u dv plus v du. We all know that. Now, if we take integral of both sides, it becomes uv equals integral u dv plus integral v du. And if we bring this on the other side, then this becomes integral u dv is equal to uv minus integral v du. This is called integration by parts. So we all know this. We'll use this frequently. So I'll just put this on the side for reference, maybe here. Okay. Okay. Now let's try to solve this. So let's say okay, so let's say this is v prime. Let me write in a different color. Let's say this is v prime and this is u. So let's write it down. V prime is e to the power minus st. So what is v? Is minus 1 by s e to the power minus st, and u is sine at. So what is u prime? U prime will be A cos AT. Okay. So let's then use this, and using this particular formula. So this is UV prime, right? So this will be UV. So sine AT is U times V minus 1 by S e to the power minus ST. Let's make sure this minus is properly there. This, okay. Limit 0 to infinity. Okay. And then this minus V du. So V is minus 1 by S e to the power minus ST, and U prime is A cos AT, and this is integral from 0 to infinity. Okay. It looks like we just, solved this, but then we are left with a bigger problem here. But you will soon see that we can simplify it pretty easily. Okay. But let's evaluate this term. Now, sine of AT when t tends to infinity, this will be a value between -1 and 1. Okay. Multiplied by -1 by S. Let me just put the -1 by S outside. E to the power minus ST. Now we will again consider S is greater than 0. So what happens is e to the power minus st is 1 by e to the power st. When t tends to infinity, that tends to 0. So the first term then is 0 minus, now sine 0 times whatever e to the power 0, sine 0 is 0. So this entire thing evaluates to 0. Okay. Now let's do this. This minus we can bring outside. So this will be plus 1 by S integral of 0 to infinity e to the power minus st times, or in fact, a also we can bring outside, cos at dt. Okay. So this we can eliminate this. So this is a by S integral of 0 to infinity e to the power minus st cos at dt. Okay. Now let's reapply what we learned here. This guy. If we reapply this one more time, let's see what happens. So let's say we assume this as V prime. We assume this as V prime and this as U. So V prime is e to the power minus, just a second, V prime is e to the power minus st. So what will be V? So we take an integral, so minus 1 by S e to the power minus st. And U is cos of AT. So U prime will be minus A sine AT. Okay. So now let's use this to solve the integral. So this becomes A by S is outside. Let's open up a bracket. So first thing is UV. So U and V. So minus 1 by S e to the power minus st times cos AT. This is evaluated from 0 to infinity. And then this minus V du. So integral 0 to infinity V is minus 1 by S e to the power minus st times du, u prime, is minus a sine at dt. Okay. Now let us evaluate, and we close the bracket. Now let us evaluate this part. So a by s is outside, minus 1 by s e to the power minus st when t tends to infinity and s is greater than 0. This will go to 0. Okay. Minus at when t tends to 0, this tends to 1 and cos 0 tends to 1. So this will be minus 1. Okay. Minus, let's say we combine these two, minus minus is plus, so still it's minus, and we bring a by s outside the integral sign, 0 to infinity, it becomes e to the power minus st times sine at dt. Okay. Now let us evaluate this part. So f of s is equal to, so this is minus or 1 by s, so a by s square, minus, if we multiply this, a square by s square times f of s, because we did see that this particular integral is nothing but f of s, right? So just bring f of s that side. So this becomes 1 plus a square by s square equals a by s square. Or we can say f of s is, if we multiply by s square both sides, a divided by a square plus a s square. Okay, obviously s is greater than 0. So if you see, we then found out that when f of t is sine at, then the Laplace transform is a by s square plus a square. Okay. We'll just move this table a little bit somewhere here. Okay, so we did good. Now, same exercise I will encourage you to do with Laplace transform of cos of at. But if you do the solution, you'll find that Laplace transform of cos of at is s by s square plus a square. Okay, so we'll continue to build on this table with few other functions, but for now I will close the video for this session and then continue in our next video. Thank you.